Presented by Caltech.
This picture shows a very simple device that acts as a valve for electrons. First of all, let me explain what the picture means. So the top picture here shows a cross-section through the silicon chip. It's as if you cut through the chip and took the front half away and looked at it edge on. And what you see is the main body of silicon down here, then a thin insulator, which is usually made by oxidizing the silicon. Silicon oxide grows naturally on the surface of silicon, and it's one of the world's best insulators. Then on top of that, there's a region of metal. And what we've done to the silicon is in these two blue regions, we've introduced atoms that donate electrons to the silicon lattice. So in this area, there's an excess of electrons. Normally in silicon, all the electrons are tied up holding the crystal together. But if we substitute for a silicon atom, an atom like phosphorus that has one more electron, then it can donate that electron and let it go free, and it can join the other electrons and flow, acts just like a metal. So we have two such regions here. You can think of them as metals. They act just like metals. If we tip the picture just a little bit, then they'll flow in the direction downhill. Just like water, if this was water, you tip it a little bit, it'll flow downhill. But when we put the atoms in to this region, which donate their electrons, those atoms each had an extra proton down in the nucleus because they were neutral atoms when you put them in. So these regions that have all these free electrons that can flow around also have a lot of positive charge from those atoms that donated their electrons. So electrons are much happier staying in this region than going off into the silicon where there aren't any of those positive charges. That means that to try to get an electron to go from this region where it's happy along with its atoms that brought it there, out into the silicon region that doesn't have those donor atoms, is going to take energy. So we've plotted down here in the lower plot the energy of an electron right at the surface between the silicon itself and the silicon oxide. And what we see is, because the electrons are so much happier here with their donor atoms, when they try to get out into the silicon between those regions, there's an energy barrier. They don't have all those nice positive charges to keep them happy. So it costs energy for them to get out there, which means if you have one of these regions with electrons in it, it's effectively disconnected from another such region, even if they're close together. So what we've done now is create a region here, which you can think of as one of those tanks. It's a tank that holds electrons. And here's another one over here, and it holds electrons. And if I put more electrons on this one, I can make it a logical 1, and if I put less electrons, I can make it a logical 0. Now, how do I connect the region on the left with the region on the right using the voltage on some other region? That's the magic of the transistor. This left-hand picture shows the structure that we just saw with no voltage on this purple region. Therefore, there's this energy barrier which prevents the region on the left from transporting electrons over to the region on the right. But we all learned in grade school that unlike charges attract. That's the only thing you need to know about electrons for the purpose of understanding this device. So if I want electrons to be happy, I put them near positive charges. That lowers their energy. you attract something by lowering the energy to get there. So if I were to put positive charges on this metal on the top, I would make the electrons on the surface happier. They would be at lower energy because they're closer to positive charges. They're attracted to the positive charges. That lowers their energy, makes them happier to be there. What that means is the energy barrier has been lowered to the point where electrons on the left can connect with electrons on the right. If I tip the picture a little bit now, the electrons can flow all the way through, whereas before, if I tipped the picture, the electrons would stop on the left and they'd go out a little on the right, and they wouldn't connect. So this device, called the metal oxide semiconductor, MOS transistor, is the thing that's in all your cell phones, it's in all the chips in every computer. This simple device is the valve for electrons. And it's controlled by a voltage on this purple region. This purple region is called the gate of the transistor because effectively it controls whether electrons can go from left to right or not. It can stop them when the gate is closed, and it can allow them when the gate is open. So it's the gate of this valve for electrons. And that valve is controlled by the voltage on the gate. Well, the voltage on the gate is the voltage on one of these blue regions of a different transistor. So we now have the magic mechanism. The level of water in one tank is controlling the valves that control the flow of water into and out of another tank. And that's all there is to logic in silicon. And without that, we would have no information age.